Namaste. I am Dr. Neeraj Upadhyay, ready to discuss with you about the crystal field explanation of color of triaxial metal complexes. But first, let's revise our previous lecture first. The establishment of a theory doesn't depend on how much it is convincing or interesting, but how different evidences support the theory. Validity of the crystal field theory was therefore depending on the fact how the theory explains nature and properties of coordination compounds. In the last lecture, you learnt about the explanation of crystal field theory on some confusing trend of transition metals. We started the lecture with some unusual trends in ionic radii, lattice energy, hydration energy, etc. Then explained them one by one. We had seen that in most of the cases, extra stability gained during complex formation were not counted, and their count played key role in explanation of these trends. In all those cases, we were applying the concept of trend obtained in main group elements and thought will be followed by the transition metal complexes in a similar way. Crystal field theory suggested that on complex formation, compound achieve some extra stability that must have been counted during prediction of any fundamental physiochemical or thermodynamic properties of coordination compound. In this module, we will deal with the explanation of crystal field theory behind color of coordination compounds. The learning objective of this module are therefore to validate crystal field theory on origin of color of coordination compounds and to apply the crystal field theory to understand intensity of color of coordination compound. A basic understanding of symmetry concept is needed for better understanding of this module. Also, I request you to learn optics from your intermediate textbooks for the sharp understanding of the concept. When a part of visible zone of electromagnetic radiation is getting absorbed by coordination compounds, the combination of all the remaining color is seen by your eyes. But I think I should not start my lecture from this point. I know many of you need explanation of electromagnetic radiation and color. Also, you may have several other queries in your mind. For better understanding of the lecture, I will raise 10 frequently asked questions and will answer those. So, this lecture will be done in question answer mode. For better understanding of the module, I request you to watch the lecture 2-3 times. The very first question that can come to your mind is, how do we see an object? When light or electromagnetic radiation fall onto an object, it reflects the light in all the direction. When retina of our eyes observe the reflected radiation, our brain image of the object. So actually, we do not see the object, we can see the light or a certain part of electromagnetic radiation. A second question raised consequently from this point is, what is an electromagnetic radiation? What part of it we can see? Electromagnetic radiation is a form of radiant energy that originate from the source and move in perpendicular direction of it. For example, in our planetary motion, electromagnetic radiation radiates from the source sun and move in perpendicular direction of it. The name electromagnetic is given because this electromagnetic radiation contain electric and magnetic field perpendicular to each other. Electromagnetic radiation is not light of a specific frequency or wavelength, but it represents a spectrum of frequencies of wavelengths. This spectrum can carry wavelength range of approximately 10 to the power minus 18 meter to 100 kilometer with a fixed velocity of 3 into 10 to the power 8 meter per second. These electromagnetic radiations are generally divided into 7 regions of increasing energy called radio waves, microwaves, infrared waves, visible waves, ultraviolet waves, X-rays and gamma rays. We cannot see all these radiation. We can only see the visible light that has a wavelength range between 380 to 760 nanometer. It is therefore any particle having size lower than 0.1 micrometer is difficult to see by our naked eyes. That is why we cannot see bacteria and viruses. But what happens when electromagnetic radiation attack on an object? When electromagnetic radiation attack onto an object, it can get scattered, reflected according to some geometrical rules, or may get absorbed by the object. So radiation may be absorbed. I think you need to know what is absorption, why some specific frequency of light is getting absorbed by an object. An object is made up of atoms or molecules. The molecules have 3 degrees of freedom, that is translation, rotation or vibration. Out of the 3, rotational and vibrational levels are quantized. In general, when a microwave radiation is absorbed, it will be able to change rotational motion of the molecule only. Similarly, an absorbed radiation in infrared region make the changes in vibrational motion of the molecule. It is also to be noted that electrons move in their quantized electronic levels. So, the energy equivalent to the energy gap of quantized energy levels can be only absorbed by the object, neither lower nor higher of it. Electromagnetic radiation of a specific frequency equivalent to the energy gap of 2 quantized levels can be absorbed. Also, the absorption of light is basically due to interaction of electric and magnetic field of electromagnetic radiation with the produced electric and magnetic field of the object. So, electromagnetic radiation can be absorbed only if the object has certain kind of electric or magnetic field. So, like quantized rotational and vibrational level, we also have quantized electronic energy levels, as you have already seen in the hydrogen spectra. Electron of an atom or molecule may absorb ultraviolet or visible light to get excited to higher quantized energy levels. In most of the cases of compounds of main group elements, electron needs ultraviolet radiation for getting excited to higher electronic level of the same atom. If so, how color appears? As I already explained that we can see only the visible radiation. So, it is very clear that all the colors are the part of visible range and come in the range between 380 to 760 nanometer. The combination of all these waves make a white color arrangement. When an object do not absorb any color, the combination of the wavelength in the range of reflected light make it white, means object looks white. Similarly, when all the radiation of the visible light are absorbed by the object, nothing gets reflected and the object look black in color. But when electromagnetic radiation of a certain frequency of visible range is getting absorbed by the object and reflect all other radiation other than this, the combination of all other frequencies do not make white color. Instead, our brain can see the complementary color which is formed by the combination of all visible radiation except the absorbed radiation. This you can understand by using a color wheel model. When a frequency comes under green zone, is getting absorbed by the object and light comes to our eye, our brain see the object as red and not the green. The details of color and constitution of color you will learn in the module 34. Now, let us come to the point. what is the explanation of crystal field theory behind color of coordination compound. As I told you, when electron of an atom absorb energy, it get excited to higher energy level. But the absorbed energy comes under ultraviolet light. This is why most of the compounds made by main group elements are colorless. According to crystal field theory, in presence of ligand field, d orbital breaks into different energy levels. For example, in an octahedral environment of ligands, d orbitals break into T2G and Eg level. An electron of T2G level, when absorb energy equivalent to crystal field splitting energy, electron reaches to Eg level. This absorbed energy comes in visible zone. It is therefore most of the coordination compounds are colored. For example, TiH2O 3 plus absorb greenish yellow component of white light, the complementary color of which is violet, and therefore compound looks violet in color. So, the color of the compound depends on the energy of absorbed radiation or on crystal field splitting energy. But electrons cannot always undergo electronic transition. It must have to obey certain rules called selection rule. So, the question arises, what rules system has to follow for an electronic transition? For an allowed transition, system must have to follow two rules called selection rules. The first rule is called spin selection rule and the second rule is called Laporte selection rule. So, let us discuss first spin selection rule. According to spin selection rule, during electronic transition, overall spin of the compound will remain constant. That is, there will be no change in spin of the excited electron during the electronic transition. This is why compound of manganese and zinc in their +2 oxidation states are mostly colorless. I think you need a little elaboration of this. Let us have an example of MnH2O 2 plus. In the octahedral ligand field of water, the d orbitals of Mn2 plus would split into T2G and Eg level. Since Mn2 plus contains 5 electrons in d orbitals and water is a weak ligand, so on filling electrons in the splitted level, 3 electrons goes to T2G level and 2 to Eg level, making as electronic arrangement T2G3 Ag2. So, all orbitals here are half filled. Therefore, by absorbing an energy equivalent to crystal field splitting energy, electron of T2G level may reach to Eg level. But an orbital of Eg level cannot contain 2 electrons of the same spin, and also according to spin selection rule, during the electronic transition, spin of electron cannot change. It is therefore electron of T2G level in the molecule cannot absorb radiation to reach to Eg level. But there is a relaxation in spin selection rule. When the spin and orbit couples together, that is when there is spin orbit coupling, spin selection rule relax a bit. That is not part of your syllabus and you will learn this in your higher classes. Now, let us discuss about Laporte selection rule. According to Laporte selection rule, the compound possessing center of symmetry and electronic transition containing parity is forbidden. That is, in a centrosymmetric molecule, transition from Girardet to Girardet or Ungirardet to Ungirardet is not followed. Thinking about orbitals, s and d orbitals contain center of symmetry and are termed as Girardet, while p and f orbital do not contain such symmetry with respect to center of symmetry and therefore are called Ungirardet. So, according to this selection rule, S to P, P to D and D to F transition is allowed, but transition like S to D, P to F, P to P, D to D are forbidden. In other words, in an electronic transition, azimuthal quantum number L can change by the value plus minus 1. Now you can ask, if it is so, how a DD transition occurs in a centrosymmetric arrangement of octahedral if it is against the Laporte selection rule? Answer to this question will insert a new concept in your mind: static arrangement of bond. But this is not the actual case. All the molecules have 3 degrees of freedom. They can translate, rotate or vibrate. Even at absolute zero, molecules used to vibrate. If a molecule contains n atoms, total number of possible degree of freedoms is equal to 3 into n, that is 1 for each degrees. Out of them, maximum 3 are the translational degree of freedom, that is they can move in x direction, y direction or z direction, and 3 are rotational degree of freedom, that is they can rotate in all the around all the 3 axes. So, a total 3n minus 6 vibrational degrees of freedom are possible. It is therefore an octahedral molecule may vibrate in many ways. 2 such vibrations are symmetric and asymmetric vibrations. In case of symmetric vibration, center of symmetry does not break and therefore T to G to EG, that is Girardet to Girardet transition, is not allowed. But in case of asymmetric vibration, at equilibrium position of all bonds there is a centrosymmetric arrangement, while in all other position of the vibration molecule does not contain this kind of symmetry. So, a relaxation in the rule is there. If molecule loses its center of symmetry, I mean an excitation of electron from the T to G level of an equilibrium position of such symmetric vibration to EG level in asymmetric arrangement of the molecule can be done. But the chances of such transition and therefore intensity of such transitions are very weak. I have already told you that the energy of absorption depends on crystal field splitting energy. So, the factors that affect crystal field splitting energy will also affect the energy of absorption of light. So, let us handle the next question: do the factors that affect crystal field splitting energy can also affect observed color of the coordination compound? A larger crystal field splitting leads to absorption of high energy of light. Therefore, the factors that affect crystal field splitting also affect color of absorbed radiation of the molecule. You know, tetrahedral molecules show intense color than corresponding octahedral molecules. Talking about the effect of ligands, the molecules CrF6 3- by absorbing red color shows complementary color green, while the molecule CrH2O6 3+ by absorbing yellow color looks violet, and CrCN6 3- looks yellow by absorbing violet color. It is therefore the crystal field splitting of these 3 molecules are in increasing order because of increase in strength of the ligand. You should find out the energy of color of absorbed radiation by yourself for better understanding of the concept. Similarly, VH2O6 2+ looks violet in color by absorbing yellow color, but VH2O6 3+ looks violet on absorbing yellow color. This is because with increase in the oxidation state of central metal in a coordination compound, crystal field splitting increases. So, the factors that affect crystal field splitting affect color of coordination compound. The concept can further be extended to many other examples. Now, let us move to our further question: why color of tetrahedral molecules are intense compared to octahedral molecule? Tetrahedral molecule do not contain center of symmetry. Therefore, the rule of parity becomes no more valid. It is therefore transition from E to T2 level becomes allowed. Actually, there is a case of mixing of p and d orbitals of metal ion here that will make an arrangement of Girardet to un-Girardet transition that allow Laporte selection rule. When both of the selection rules are allowed, chances of transition are more, and therefore more will be the intensity of the color. Mixing of p and d orbital in tetrahedral arrangement you will learn in molecular orbital theory. According to crystal field theory, Laporte selection rule is not applicable on tetrahedral molecule, and therefore tetrahedral molecule gives intense color over octahedral molecule. We talked about D transition till this point. Do you know there is molecule of transition metal like potassium permanganate which do not contain any electron in its d orbital but shows very intense color. So, why some molecule like potassium permanganate and potassium dichromate which do not contain any electron in its d orbital shows very intense color. The molecular formula for potassium permanganate is KMnO4. Let oxidation state of manganese is X, oxidation state of oxygen is -2 and of potassium is +1. Since molecule is neutral, therefore sum of oxidation state of all the participant of the molecule would be 0. Therefore, +1 plus X plus 4 into -2 should be equal to 0, and therefore X will become +7. Since manganese in neutral state contain 5 electrons in D and 2 electrons in S sublevel, on its +7 oxidation state, manganese do not contain any electron in d orbital. So, what is the chance of transition? Actually, an electron excite from p orbital of oxygen and fall onto d orbital of manganese. As you know, p orbital do not contain any center of symmetry and d orbital contain that. So, this kind of transition becomes both spin and Laporte allowed. Since transition follow both the selection rules, it is therefore potassium permanganate gives intense violet color. This kind of transition is called ligand to metal charge transfer. Crystal field theory not only explain the origin of the color in the coordination compound, but also explain why some coordination compounds are colorless. According to crystal field theory, in presence of ligand field, the 5 degenerate orbitals split into 2 or more energy level. The color of coordination compounds appear due to transition of electron from lower energy state to higher energy state of splitting. In octahedral arrangement, the transition from T to G to Eg, and in tetrahedral arrangement, the transition is in between E to T2 level. The energy of absorption depends on the factors that affect crystal field splitting, like nature of ligands, charge and nature of central metal ion, and geometry of the molecule. All the electronic transitions are not allowed. During electronic transition, change in spin of electron is not allowed, but during spin orbit coupling, the rule relaxes. However, in case of spin and angular momentum coupling is mostly found in third transition series or in case of F block elements. Also, in the molecules containing center of symmetry, Girardet to Girardet and un-Girardet to un-Girardet transition is not allowed. It means S to P or P to D transition is allowed, but P to P and D to D transitions are forbidden. But most of the coordination compound in octahedral geometry are colored, which is because of break in symmetry due to asymmetric vibration, and the transition that occur in this period is called vibronic transition. The compound that obeys both the selection rule are intense in color. Tetrahedral molecules obey both the selection rules and therefore form more intense color corresponding to octahedral molecule. So, it is to be noted that intensity of color of coordination compound is not related with the crystal field splitting, though it is related with allowance of electronic transition. A coordination compound that do not contain any single electron in its d orbital may be colored and even with more intensity if it obeys both the selection rules. Potassium permanganate is intense purple colored compound with empty d orbital. This is due to ligand to metal charge transfer. So, I hope you have learned this lecture. Thank you very much for listening me.